Ahora sí.
A ver si...
No petaba aquí, pero...
Era aquí, ¿vale?
Sí, en la sede.
Sí, y ahora está puesto aquí. Ahora se ve aquí lo de la transmisión.
En la reunión de aquí. Vale.
Y aquí está.
A ver, si te vas al otro sitio ya... Vale, maravilloso.
Vale,
Aquí, desde aquí lo veis.
Está guay que haya salido, pero maravilloso no es.
Una movida.
No, es cierto, es cierto. Pero bueno, ya está, está apuntado. Ya no...
Muchísimas gracias.
Nada.
Sí. Para decir a estos chicos que ya estamos...
Oye, ya van a entrar.
Hasta luego.
Voy a pasar al
Sí. Es que para que se grabe más fácil. Bueno, más fácil no es. Pero así nos evitamos tener que subirlo luego.
Sí.
Es un rollo. Sí. Nos han quitado ya la galletitas estas, ¿no?
Puedes pasar si tienes una foto de tu póster. Creo que se la hice, pero no.
Te paso el PDF. Se lo pasé a Adam y estoy leyendo Next Round, Galicia. Por lo de que estuvimos jugando al blanco. Y te dijo lo de Galicia.
¿Pero qué has dicho de Adam, perdón?
Que me está pidiendo el póster.
Ah, por el formato. Sí.
Ah, ¿qué quieres? El...
No, yo quiero el
PDF.
O sea, para verlo.
Vale, pues pensé que estás hablando para Adam, sí.
Y se lo pasé a Adam y me metí en el chat de Ama y ponía Next Round Galicia de cuando estábamos jugando al blanco. Y que alguien dijo ballenas, ¿no? Algo así.
Estoy viendo esto de...
Esta gente se conectó. Guys, do you hear us?
Yes, but
Yes.
you were having some debate about
Yeah.
posters and Galicia.
Presento yo, Oscar.
Ya está pendiente de que grababa.
¿Grabamos por si acaso o confiamos en el directo?
Yo confiaría en el directo, ¿no?
Vale, confiamos en el directo. Ok. Te hago la presentación aquí, ¿eh?
Sí.
Okay.
Sí.
Hello everyone, welcome back to the trading group week. It is my pleasure to announce... me quedé en blanco. Manuel López Medel. Sí, se repite. Hi everyone, welcome back to the reading group week. It is my pleasure to announce Manuel López Medel. And he's going to talk about integrability of algebroids 3. So it's the third part to a series of lectures imparted by Asia. So thank you very much, and the floor is yours.
Thank you, Ruben, for the presentation. Yes, now this is the third lecture of the integrability of Lie algebroid. I'm going to continue with the explanation of the previous lecture of the main theorem of Kreinig about the integrability of Lie algebroid. Well, now this is going to be the lecture 4 of the notes of Kreinig and Riloya of integrability of Lie bracket. And well, in previous lecture, for any Lie algebroid, we have constructed the one-state groupoid B of A. And this one-state groupoid is the algebraic analogous of the universal cover of a Lie group. It always exists as a topological group, but is not always a manifold. So the obstruction are the elements that prevents this y-axis groupoid from being a manifold. And we are going to remember which are these two obstructions, because in the previous lecture we write the theorem, and now I'm going to remember what it's about. Well, another thing I want to say is that a necessary condition for A to be integrable is that the monodromy group must be discrete. So we are going to use that to answer this question. What are the obstructions? To integrate a the algebroid. Okay. So the main theorem said that for A, the following statements are equivalent. One is that the algebroid is integrable. The second is that the y-axis groupoid is smooth. And the third one is that the monodromy group are locally uniformly discrete. Okay. In this case, the y-axis groupoid is the unique simple, well, simply connected Lie groupoid integrating okay. Well, the meaning that the monodromy groups are locally uniformly discrete has a meaning that is actually longitudinal. Fixing a norm on each fiber
Yeah, sorry, could you write bigger letters?
okay. So we fix a norm in each fiber A sub x, which varies continuously with respect to x. We use it to measure the discreteness of the monodromy group. Okay, so we measure the discreteness of the monodromy group as follows. As the distance from 0 to the monodromy group without the 0. And also assuming that if the monodromy group is trivial, the distance of this is infinity. Yeah, is infinity. Okay. The group is discrete if and only this quotient is greater than 0. Okay. So if the monodromy group has an accumulation point at 0, the groupoid will fail to be a manifold even if we restrict to a single leaf. We can also name this quantity as the radius of this green line. And now with this, we can rewrite the main theorem as the next one. Again, if we have a Lie algebroid over M, is integrable if and only if for all elements in M, the following condition holds. Okay. The first condition is that the radius of discreteness must be greater than 0. And the second one is that the limit infimum of the radius of discreteness must be also greater than 0. Where y converges to 0 with y outside the orbit to x.
Why converging to X, I guess?
Oh, sorry. Yeah, thank you. Yeah.
And why is a sequence? Okay.
Mm,
No, sorry. It's okay, sorry.
Okay. Well,
And maybe the screen is actually not seeing you, no? Like the camera. So can you go up here and then move back? Well,
Va con retraso ese.
sí.
Okay.
Okay. So now we are going to say that when we are in the same orbit, the first condition can be seen as a longitudinal condition, and the second one can be seen as a transversal condition. So so we have that the monodromy group are equivalent whenever S and Y are in the same orbit. One is a longitudinal abstraction. And two is a transversal abstraction.
And you mean 1 and 2 of this theorem?
Yeah, oh, sorry. Yeah. Thank you. Okay. The second condition tell us that even if every monodromy group is discrete, the algebroid must fail to be integrable. Because it can make the radius of discreteness to convert to 0, causing the topology of the Weinstein group point to be non-smooth. So I'm going to write it. So this convert to 0. Yeah. So this limit, the limit of the infimous, is taken over points y outside the orbit of X. Inside the orbit, the radius of discreteness is constant, and the longitudinal part is stable. If both conditions hold, as we are going to see later, the Weinstein groupoid inherits a smooth structure from the Lie algebroid, and it becomes the unique simply connected Lie groupoid that integrates the infinitesimal data of the Lie algebroid. Also, I want to remark that the transversal obstruction, the second one, is not a stable condition. In a related neighborhood. I mean, a neighborhood without the 0 element of a point without being true at the point. This comes from the fact that the radius of the treatment is needed upper, not lower, semi-continuous. Now I'm going to remember quickly what is the meaning of being lower semi-continuous. So a function from f to the compact closure of R, sorry, with the infinity is lower semi-continuous. Semi-continuous at a point x0 if and only if the limit of x to x is greater or equal than the image of the function at the point x0. Yeah, so we can have a sequence of leaves where the monodromy groups are well behaved. So the radius of this cleaner is large, greater than 0. By this suddenly collapse or explode at the limit leaf. Because of this, we can have a non-integrable algebroid that is the limit of the integrable one. Okay. Well, now I'm going to continue with an example of previous lectures that I said show us last week. So we consider the first two as the with the structure, with the same structure as in the previous lecture, with the modified Poisson structure. The Lie bracket of the cotangent Lie algebroid of SU star is as we defined in the previous lecture. And the anchor so we consider Wheeler scale the anchor by rho of A equals 8 times 4. Now we restrict to the sphere of radius R.
Sorry, the Lie bracket also changes. Like the one you wrote is for the standard SU2,
Yeah.
And it's dx dy is equal to dz plus something that depends on this factor a. Yeah, exactly.
Yeah, thank you. It's also the style. Okay. So now we're at 3. As we saw in the previous lecture by Aster, the monodromy groups are given by a function depending on the radius, the integers, and the unitary vector. Okay. And also we said that if the function has singularities, the monodromy may vary in non-trivial ways. Okay, now we are going to compute the radius of discreteness. So we have, as I said before, to have a norm in the fibers. So we choose the Euclidean norm. In the fiber. Sorry. Okay. And now let's do the computation. Well, because as we can see, the monodromy groups are discrete and also cyclic, is generated by the next element I'm going to write. Okay, so the radius of this field in this case is going to be the Euclidean norm of this element generated by the by this element. Because the Euclidean norm of this is R, we have that the radius is 40 over R. Yeah. And we have that we have that if the derivative of the function a is different to 0, the radius of this unit is going to be this quantity, but if 0 is going to be the distance, as I put before, to the trivial group, so it's going to be infinity otherwise. Okay.
Sorry, this A is the integral or
Yeah, it's the integral, the computation that as I did in the previous lecture. Well, so actually, if this derivative is non-zero, is different to 0, is that the symplectic area is changing as one moves transversely across the space. So the monodromy group is a discrete lattice in the 1D isotropy algebra. And the radius of discreteness is going to be greater than 0, but it is 0, the variation of the symplectic area is 0, so the monodromy group is the trivial, actually. Okay. What happened in this example is that the radius of discreteness is not upper semi-continuous at the critical point of the symplectic area. So with the obstruction that we have for not being integrated this.
Sorry, just to make sure, what do you mean by symplectic area?
If the function a of r that we saw in the previous lecture, I don't have the formula of the, I didn't write it, but it's the integrable of, I don't remember right now.
It's something that depended of this lowest case A that was the factor that we modified the SU2 was, and honestly the other day I also didn't write it fully because I think there is some mistake in the lecture notes of Ruiloya and Kreinitz because either this A of R was wrong or the remember that to calculate this, we used this curvature of the splitting and stuff. So there must be some mistake in that lecture notes because they didn't match those two things. That's why I didn't write it. I think the other day neither.
Yeah, but I would just say that the SR is a symplectic submanifold of our Poisson structure, so it naturally carries a symplectic form, and what you do is just integrate it.
Yep.
Okay. I missed it.
Okay. Yeah, so well. Yeah, I'm going to follow with the well. Yeah, the case is that the radius of this discreteness, yeah, is not upper semi-continuous. At the critical point of her. So in the points when the derivative is 0. So if we have a function a of r such that a prime of r converges to 0 at the r converges to 0, the radius of discreteness vanish at the limit. So it happens that the limit of the infinite of the radius of the discreteness is going to be 0, as if you remember, the this radius must be greater than 0. So we are having the second structure, so we don't have the integrability result. And also we can say that this is an example in where the monodromy group is discrete everywhere, but it's not uniformly discrete because of this. So the Weinstein groupoid is not smooth. Okay. Now I'm going to follow with another example. I want to write the sample first. Okay, so we consider the manifold M as the sphere times the quaternion. So, better. Okay. Well, what I want to say, what in the lecture's note want to say with this example is describe a Lie algebroid where the geometry changes between two regions, yet the integrability condition is going to remain. So the collapse is not going to be as abrupt to be that's equal to 0. So we are going to have the two condition for satisfied integrability. So in this example, we are going to have integrability even if we have a chain in the geometry of two different regions. So we take the real algebroid as a vector bundle of rank with basis E1, E2, E2. Well,
So a trivial.
sí,
Okay.
trivial rank. Sí. Yeah, and also the linear and the anchor well, these are the vector fields on the sphere and this in the linear action of the quaternion. The behavior of the anchor defines two orbits for the link.
Which vector fields on the sphere?
Well, not I will say
Maybe the ones of the SO3 action or something like
yeah,
that.
sorry, yeah, the rotational, the rotational, I was better to write than not to. The standard rotational. Vector fields on S3. The W white linear action on the pattern. I think the canonical exactly. So the anchor behavior of A in the case, well, injectives on outside the origin and is not injective, the anchor is not injective on the okay. So yeah, the monodromy group yeah, is well n of no, how do I n okay, so in the first case, the monodromy group is going to be the trivial group, and in the second case, is going to be the integral set. So yeah. So in this first case, we are going to have the radius of discreteness to be infinity, and in this is going to be R0. It's going to be an integral greater than 0. Yeah, so we don't have the longitudinal obstruction in here because the two quantities are greater than 0. For the transversal obstruction, that will be the limit of the infinite. Well, this if we take an element of this orbit, we approach it from the other leaf as this, and because the values of this are all infinity, the value of the point is going to be in x R0, so the limit is going to be greater than the R0, so in this case we don't have the abstraction. Besides, we have that chain of geometry of well, so we don't have that problem. So there are no abstraction, and we have that the Lie algebroid is integrable. Okay, now we're going to start with the proof of the theorem.
I guess this is an action groupoid, no?
Yeah,
Sure. I also wanted to comment that. Yes, as Ruben said, maybe you.
No, I mean, I just rotations, no? On the sphere and the quaternion.
Yeah, and the interesting point here is that these vector fields, if I'm not mistaken, right? I think they are complete.
Yeah.
Right? So even in the non-complete case, we know that always this before Lie algebroids, this integrates to a locally group action. This is a deep result complicated by Palais. So if we have a Lie algebroid like this, it will be always integrable. So just
Okay.
that comment. And even in this case, it is more easy somehow because the vector fields are complete. So they come from a global Lie group action.
Okay. Thank you. Okay, so yeah, we enter now the we are going to start the sketch of the proof, and we are going to be saying something of the proof. The first thing I want to comment is the smooth structure of the one-state groupoid. And yeah, to establish the smooth structure of the one-state groupoid, we have to we ensure the space of a path with the structure of an infinite dimensional manifold. Okay. So P tilde of A is going to denote the manifold of P1 curves from I to N whose base start gamma equal by R of plus 2. Okay. And there is a lemma that says that the space of A path is a submanifold of this space I defined. Okay.
So manifold is like this. These are Banach, let's say.
Yeah, exactly. It is Banach. I omitted, but yeah, exactly. It is Banach.
And the submanifold is also Banach submanifold, no? Okay, yeah, yes,
Yeah.
I see.
Yeah. So, given a PM connection on A and it associated a connection denoted with the same number, the tangent space. The tangent space of the A path at A consists of pairs. Sorry. Representing vertical and horizontal variation, satisfying the linear A path equation. Okay.
Sorry, why the tangent space to PA consists of such pairs? Is it like obvious or?
I guess you would take a curve of 8 paths, like a one parameter family of 8 paths, and taking the derivative of that, you get that equation.
Yeah, I think.
Yes,
So-
probably
Yeah,
something like
I
that,
guess.
plus this condition that we needed. We had this morphism that a path has to be a morphism of Lie algebroids, which was equivalent to a certain PD with a connection. So probably combining those stuff to get to that.
So in the Banach case, the tangent space is a question, right? It's also this space of tangent vectors too.
Yeah, in the
Also in
Banach,
the Banach case.
in the Banach case, yes.
Thank you.
Okay. Yeah. Well, I would also like to remark that, well, this also said that, well, that's a remark. The resulting, well, the Wednesday group of G of A, if it is smooth,
So are these paths also no, not smooth, but what class are of these paths? U and phi?
of the A path are of the
They're C1 or C0, I guess, but
I guess the U and phi are also C1 and C2.
yeah, I think
Maybe
that
I'm
they are.
mistaken, but
okay. Okay.
Okay. Well, so if the Wednesday groupoid is going to be if it's smooth, finite dimensional manifold of dimension, the dimension of the base M plus the rank of A. Okay, well, this is now. A definition. To be more precise about the smoothness of the Wednesday groupoid is that to say that it's smooth, if that means a smooth structure with the property that the projection of the A path to the Wednesday groupoid is a submersion. Okay. By the local form of the submersion, the smooth structure on the Weinstein groupoid, if it's a 6, is going to be unique. And also besides, if we are, besides we are in an infinite dimensional setting, there are no problems in our case because the fibers of the projection map are submanifold of the set of A paths of finite codimension. And this also is going to appear in the next section.
Sorry, could you show some examples? I mean, one example.
Of this, I actually don't have any example right now,
Okay.
but I think I don't have right now. But maybe I can find one and send you.
Yeah, sure. It would be grateful.
Okay. Okay, now we're going to describe the equivalent classes of the homotopy as the leaf of a relation. So the relation of the homotopy as the leaf. And for on the set of a path of finite codimension. So the one state groupoid is the leaf space of a relation of a relation. The relation is of. Okay. So we also are going to use that the connection of nabla associated to nabla commute with the anchor. Yeah. So
Sorry, nabla without bar is a connection on TM, and nabla bar is connection on what?
in I think in the a path, right? Or I remember well. No, sorry. Nabla is the connection on TM,
Mm-hmm.
and nabla bar in P A. No. It is when you have a TM connection on A. Nabla bar, I was checking the lecture notes. Is the
It's also
connection on A? Okay.
yeah,
Induce a
connection. Mm-hmm.
Okay. Yeah. Thank you. TM connection. And a connection on TM, right? A on A. Yeah, sorry. Okay. Thank you.
Sorry, could you fix the camera?
Sorry. Yeah.
Thank you.
Yeah. Okay. So now on the so for the path number. In N, we consider in okay. Definitely. Yeah. So as we say, well, no, given a path with main with the Ghanaian vector. Okay. Given by okay. And now we are going to, well, we define just this tangent vector in this tangent space of the space we define it in the blackboard. And now, by this lemma, we are going to see the geometric interpretation.
So phi is gamma. Or
This
maybe
this gamma is the point, well, is the path base.
so P is such that at each time it lies at the fiber of gamma t, no? It doesn't matter. It doesn't matter.
We take an element of the space of a path with tilde
Yeah.
and the a path,
Okay.
and then with this pair we define the vector phi such that the components of the vector phi satisfies the equality.
Okay.
Well, maybe by the lemma it clarifies a little bit more. The vectors we just defined are tangent to the set of a path, and they do not depend on the choice of on the connection. more precisely, using A and B satisfy the homotopy condition. That's the let's see. Then okay. So giving as a remark, giving A0 and B0, we can always extend them to families A epsilon and B epsilon, satisfying the required condition. And also for some time-dependent section, we can have a vector solving this question. So we can extend to a time-dependent section. This is written in the lecture note, but I'm going to skip this part for a moment. Okay. Yeah. Well, so we are going to continue with our purpose to realize homotopy classes of A path as leaf of the ovulation of the A path. Well, of the set of A path. So A path as leaf of yeah. By definition of the homotopy, we have to restrict to path in vanishing at the endpoint. So for a path gamma in M, we consider the zero gamma tilde of A like that. Yeah, and now we define that the distribution on P of A goes by that at A is given by now if we have a family of A path is a homotopy if and only if the path let's go from epsilon tangent to the distribution. Until A path are homotopy if and only if they are connected by a path tangent to the distribution. Okay. D is integrable where is also an involutive distribution. Yeah. This is also an involutive distribution. So there exists a foliation integrating it. And I'm going to write it in the next lemma. Interpreting el plan de distribución. define one action of the algebra. So in particular, the distribution is involved.
Sorry, P0, P0 is the isotropy.
Yeah, I skip that,
Okay.
but yeah, I can write it. So it's the algebra. I don't know if it's clarified or.
Yeah.
Well, so the main properties of the relation in integrating the distribution are united in the theorem that says that for a linear algebroid. Axis. Yeah, the last says that two paths are equivalent if and only if they are in the same leaf of the variation. Okay, now let's go. We are going to talk about the exponential map. For a Lie group with a Lie algebra, the exponential map is a local diffeomorphy around the origin. Well, so the smooth structure of on the Lie group around the identity element can be obtained from the Lie algebra and the exponential map. So now we're going to do like an analogous. Okay, so let's consider a Lie groupoid and a Lie algebroid. In this case, the exponential map will require a choice on the connection. Yeah. Now we take the pullback of nabla along the target map. This define isomorphic to independent of the portable. Well, this connection is denoted by nabla over X and so on a neighborhood is equal to so without it and we extend globally what sigma by putting together
Sorry, Manuel, can you walk back and then?
You prepare to sit here.
okay. So this map is a diffeomorphy from an open neighborhood of the third section. Do an open.
So I have a question. I have a question. The exponential, as far as I recall, you could define for sections of the algebroid.
Yeah.
So you took a section of the algebroid, like make the corresponding translation to the right translation to obtain the right invariant vector field, and then exponentiate the, so take the flow of that vector field, which in general could be non-complete, etc. So, but I'm curious on how you make it pointwise just by taking the connection.
Okay, so from this to this, right? Or no?
Like how do you define this exponential?
Yeah, okay. Yeah, exactly. Yeah, it's yes, I'm reading the entry, and it's an abuse of notation.
Okay.
Actually. Yeah. So yeah, as you said, they are defined on a neighborhood of the origin, and then they write it in the entire fiber,
Okay.
and then they put all together in a global exponential map.
Okay.
Yeah, but they don't give. I think that they don't give any explicit formula. But what they do actually is to extend to to another exponential when for the Weinstein groupoid, besides not being the Weinstein smooth, and then they see that the definition of this exponential and the one is I will should write later is going to be the same.
Okay.
But I'm really out of so or
Whatever you want.
Hay curiosidad.
Maybe you can give some concluding remarks or
yeah,
something like that.
yeah, I was
Okay.
thinking of that. Not giving the full
Yeah.
yeah, so well, I'm going to continue by speaking.
Yeah.
Yeah. Yeah, so as I was saying, they define this exponential and then they define another exponential for the Y-state groupoid. This exponential for the Y-state groupoid is done even if the Y-state groupoid is non-smooth. And then they see that the two exponential math are the same. And well, this is written in the lecture note, so I will also write it with even with more detail. Yeah, so I will do some, for example. So some last result, for example, this corollary is integrable. Then is injective. Y te va a ese grupo de piezas, ¿no? Okay, so la bien. For any local connection, the exponential map. Pues, translate. And lastly, v of a is smooth if finally exponential is injected around the zero section. In this case, it's a little integrating. Okay, so I skipped a lot of things about the exponential, but it is written in the lecture notes, so you can check it, and if you have any question, you can ask me.
Okay.
I'm sorry for the delay.
Okay, so sorry. Oh, yes, thank you. Thank you, Manuel. Are there any questions here or in Poland?
I have one. Maybe it's a silly one, but when you're defining this distance for the case of the monodromy groups, you say, okay, you choose a norm on each fiber, which varies continuously with respect to x. And I guess that everything does not depend on the choice of the norm because as each fiber is a finite dimensional vector space, on each fibers they are equivalent, and then since it varies continuously with respect to x, it doesn't matter. The choice of the norm, right? Is something
Yeah.
like that? Or-
Yeah, I think so. Yeah, it's actually our remark. Yeah. Thank you.
Any further questions or comments? Maybe there was.
Well, yeah, adding to the previous question, yeah, it's precisely that. Like you can just use the local trivializations, the Euclidean norm, and glue them with partitions of unity. That's what it said on a footnote of the lecture notes.
Thank you, Chef.
Thank you.
Well, if not, I think we can thank Manuel again. So, and then let's stop this. So I don't know if you noticed, but we have an unexpected visitor here.
Yes, yes. Around.